kick it off with the Pragmatic Pwn of ICS, Engineering and Cyber Skills to Understand and Attack ICS. So please welcome Bryan Singer.
Thanks, Jeff. Appreciate it. Would you like to chair up here, or do you want to stand?
I'll stand.
There you stand. Okay. Good morning, everybody. Well, I don't know about y'all, but I'm more of a crack of noon type, so this getting up before 8 is really a little bit tough. But that was a very good lead-in by Dale. Thank you very much. And yeah, I think that actually that's a really good point to bring up, talking about we need to be looking at, well, how do we keep moving forward? About 16 months ago or so, I actually did about, I don't know, a couple of dozen different facilities all over the world for one particular company. They had a lot of power generation, pipelines, had a number of different facilities. And what we were doing for them was disaster recovery planning. So we were doing like minor assessments, and we were going in and creating scenarios, and then we were working through with their folks, well, hey, here's what would happen, what would you do about it? And it really struck me that a lot of the folks in the room didn't really buy what we were saying at first. It's like, oh, well, we have a machine overspeed protection, there's manual valves, there's this, there's that, there's these safety systems. You're not going to be able to do this. So I'm really not one to be outdone, so I brought along some engineers that actually knew this stuff really well and a lot better than I did, and we started going, no, wait a minute. If you did this in this order, in this step, if you actually bypass this valve, or if you overwrote this firmware, this is what the next step would be. And so the next exercises we did had some fairly wide eyes in the room. And so that was where the S4 presentation last year really came from, was the idea of saying, hey, look, we need to make people understand that this is not, I'm an IT person by trade, okay? I'm not an engineer. So guess what? That's why we bring engineers along with us whenever we try to do these projects now. So Lily Glick, she has spent a lot of time in distillation columns, which is going to be our scenario for today. And so we brought her along so she'd be able to go through a lot of what an actual engineer would look like. So really quick, today what we're going to spend our time on are basically 3 areas. We're going to talk about how do we assess and design a process. What are the things that we look at now from an engineering level perspective? I'm going to spend very little time, in fact, almost none on cybersecurity, because I look across the room, and most of you folks know this as well, if not better than I do, right? Now, so we're going to spend a little bit of time on the assessment. Then I'm going to talk about, once these processes are in place, what are the additional things we need to be looking at from a network security monitoring and intrusion detection perspective. So in other words, once these systems are running and we know what those threats are, what are the other things that we ought to be doing to make sure that we're maintaining a safe and reliable operation? And then we're going to talk a little bit about when things go wrong. Well, guess what? There's a few forensics folks. I've spoken about forensics here before at S4. So there are folks here in this room that know that. So what are some additional considerations that even I've learned that say, all right, fine, what are some other pieces of data that we need to be gathering to help us figure out who did what? So we're going to talk about how to own an industrial process, and we're going to use a distillation column as an example. Just talk about really quickly here. So we'll be beginning with a PHA and a process analysis. How many folks know what a PHA is in the room? Right, exactly, right? So in other words, a PHA is a process hazards analysis, a basic engineering discipline that will be done by pretty much any engineering process that has potential safety threats, and that's how we're going to identify the worst case scenarios. What are the things that may actually happen that we need to be worried about? So we're going to understand the threats of the process. Then we're going to work on understanding what alarm and events and communications are used to monitor a process. What are the operators looking at? What are the engineers looking at if they're trying to understand whether or not a process is operating safely? Then we're going to try to understand the various safeguards that may be put in place, including manual and online controls. And we'll talk about this. I've seen entire manual processes that were completely hackable. Well, we'll talk about how that could be. All right? And then we're going to talk about how would we model the bypass mechanisms. How would we get around some of those controls if somebody was actually trying to attack, and the engineering steps that are required. So with that, we're going to talk about a distillation column, and it all begins with a PNID. And I got asked several times, are you guys going to show a PNID? So here's your PNID. However, that said, if anybody's seen PNIDs, piping instrument diagrams, they tend to be this big, very complicated. Lily was very kind as to produce one that we can actually read kind of on PowerPoint. So this is what they look like. So what I like to do is I will turn it over to Lily so she can run us through what does the distillation column do. But really quickly before I do, why did we pick a distillation column? The reason for this is pretty simple. Number one, I don't really want to stand up in front of everybody and tell you what a very major mass casualty potential type scenario is. Distillation columns, even though we might be processing various flammable chemicals at a high temperature and there may be some risk, tend to actually be fairly safe because if they're well designed, they're going to have a number of controls in there that make the very maximum damage, the maximum damage type scenarios to be fairly unlikely. However, in any given process, the distillation column can represent as much as 40% or more of the energy used for an individual plant. So obviously, if we're able to impact one of these in various ways, we can cause extreme financial impact to an organization. So I can already start to think of some various ways that people might want to try to cause inefficiencies in an operation like this. So we're going to talk about that a little bit. So with that, this is our piping and instrument diagram, and we're going to turn this over. And so Lily is now going to walk us through a little bit about what a distillation column is and what it does.
So the point of a distillation column is to separate your feed, which is a mixture, into its more pure components. So the liquids are going to go down to the bottom of the tower, where they're going to be sent to a reboiler, and they're heated up using steam or hot oil. And some of them are going to be returned to the tower as vapor, which will heat up the tower. And the rest of them will be sent off as bottoms, and they will be used for further processing or be sent off to blending or products. The vapors that go up the top of the tower are going to be sent to a condenser, which are cooled using cooling water, which is typically about the same temperature of the atmosphere. And then we are going to accumulate those in the reflux accumulator until they're pumped into the reflux, which goes back into the tower, and the distillate, which goes off to further processing or products.
Okay. I don't know about you guys. Every time she has every practice we've done so far, she said reflux accumulator. I keep thinking she says flux capacitor, but anyway. So okay.
So we're going to talk about an ethanol water mix. So we thought we could talk about a benzene toluene mixture, but that's not as fun as talking about a vodka distillery. So we're going to be making 80 proof vodka, and after we've separated out the methanol, all the solids from using our fermentation, we're left with about 10% ethanol water mix. So that's sent to our distillation column, and because ethanol has a lower boiling point than water, it's going to be sent up the top of the column, and we're going to be sending some of it back as reflux, and then the rest is going to be set off as our product. Okay. If we wanted to make more than 80 proof vodka, say we also had a product that's 100 proof, we would increase our reflux to try to get a more pure product. And then we're going to be sending water off as our bottoms. Okay.
And just really quickly, the P&ID drawing you saw a moment ago, well, obviously that's going to be with the drawings that you're probably handed when you go to start an assessment. But if you go out and you look at the HMI screens, most likely the HMI screens are going to look an awful lot like this. And they're going to show you, again, they're going to show you what's going on in a various column. Inside that column are a number of trays that allow the separation of the various weight materials. And then obviously you're going to have your various valves and all those things. Those will be shown there. And then operators are going to look at statuses. They're going to click on those valves, and that's how they're going to interact with the process for the most part. So again, we showed you what the P&ID would look like. Now we're showing you a little more about what the operators would see. So we're going to start moving into now, if we were called in to do a cybersecurity assessment, and this was Lily and I executing the project, me as a cybersecurity person, her as an engineer, these are the things we're going to look at. So we're going to start with looking at the hazards in the process. So right away, Lily?
First thing you would think of is what happens if you increase the steam. Steam can be pretty dangerous because it's going to overtemperature your column by increasing the amount of vapor that you create from the reboiler, and that's going to increase the amount of vapor that's created inside of the tower. So you're going to have an increased flow over the top of the tower, and that may mean that we're not able to cool all of that down into liquids in our condenser. So we can have an increased amount of pressure in the reflux accumulator, and we might open up the control valve to release some of that to the flare, and that's burning off our product, and we can't sell it, so that's losing money right away.
So obviously, you think about it, if you've ever been to buy an oil and gas refinery or a vodka distillery in this case, you see that big flare that's going out there all the time. Well, that's product that's going out that's not going to be used. Now, the flare is obviously a normal part of the process, but again, if you're venting to flare, that's an expensive part of the operation. So I don't know, if you obviously look at, like, if we were to open this valve here on the bottom left that's highlighted in red, that would be how we would increase temperature into the reboiler. We increase the steam, correct? Okay, so when I think about steam, obviously I think about pressure. So now, if we're increasing the steam in there, we're raising the pressure inside that column. Could that potentially result in an explosion in this column?
Well, typically, or all of the distillation columns that you'll see will be fitted with a pressure relief valve that's shown up at the top. That's going to open up mechanically whenever anything happens that is overpressuring the column about a few pounds over the maximum allowable pressure.
Okay. So again, I think if you look, that's a mechanical valve up there. So that's something we would look at in a well-designed process. We'd understand, well, the possibility of actually creating an explosion type scenario off of this based upon increasing the steam, probably unlikely if it's properly designed. Well, she'll mention a couple of things to consider when you're doing that. But again, if you look at this now, so from a cyber attacker perspective, well, if I want to increase steam, this may be something I would do down here. But even though I may cause, I mean, what are the other things that could cause? We talked about, like, we could cause a premature failure inside the distillation column, which could result in extended downtime and increased costs for the operation. So obviously, we could cause a lot of financial impacts, but we're probably not going to create a very dangerous scenario as a result of this. Okay? So
like I said before, you're going to want to increase the amount of reflux you're using if you're wanting to get a more pure product. But say that we're not selling more than 80 proof vodka, then we're just making useless product, and we're going to have to be spending operator time to water that down and make it something that we're actually going to sell. So that's just wasting our time and thus wasting our money.
All right, now, so again, we're looking at this. If I was to try to conduct this, if I was to try to conduct this as an attack, obviously my objectives are to try to gain control over a couple of those valves that are highlighted right here. So now, let's say one of these was an online valve and I could trip it through the HMI, but what if one of them is a manual valve? What may be something I could do if I wanted to cause somebody to maybe go open that valve for me?
Well, you're always going to be having a lab that's going to be testing your product. It may only be every 6 hours or 12 hours, but you could fabricate the lab results and say that you're not getting a pure enough product, say you're only getting 70 proof, then your operator is going to say, hey, we need to increase our reflux, that way we're getting the correct amount of product.
So again, I think that's when we've done a lot of modeling, we've said, hey, are there alarm conditions, and there's folks here that understand this pretty well, are there alarm conditions that we could set in other areas of the plant that would have an operator go out and take the action that we want them to take? So just because it's a manual valve or just because it's a manual control does not mean that an attacker wouldn't be able to somehow cause you to go out and do that manipulation. And these are the types of things that we have to consider when we're doing our assessments. What would be the objective of the attacker? And if they're going to do these kind of things, now, do I need to make sure I focus a lot more on my operator messaging? An example I bring up of this is I was working at a hydroelectric dam a number of years ago, where basically an operator would get an instruction, 200 cubic meters per second, or per minute, no ramp, and he would go up and pull a lever. That operator would do no verification on the alarm whatsoever. And in fact, actually, they had this very problem where a number of years ago, they opened up the spillways too quickly and they ended up flooding a recreation area and killing some people. And so they knew very well what this meant. And I said, and you still haven't actually thought about the fact that you might want to have verification of those operator instructions and not just have the operator pull that lever. Because what happens if I can actually send you that command and then cause you to go open that up without any consideration? And they would, you're probably right. So after that, they instituted a procedure that they would actually call the scheduling office and verify the command before they executed it. So, okay. So anyway, so continuing on to some other potential hazards.
One of the biggest hazards that I would think of would be overfilling your tower. You don't always have your pressure relief valve fitted for the maximum maximum pressure that you can create. And one of the ways of doing that is filling up your tower. So by closing off all of your valves that are the outlets from the tower, you're going to overfill your tower quite quickly, and the operator may not have enough time to respond to that.
Okay. And so if I flood my tower, what are some of the things that may be the result of that?
So earlier we talked about the trays that are inside the distillation tower. Those will get damaged if you're flooding your tower, and once they're damaged, you need to shut down your process and fix those. And contractor time is expensive, and they aren't working very efficiently. So it is going to be pretty costly if you have to shut down.
So the thing that comes to mind that we might want to watch out for here, these are scenarios that some of us that have done assessments have heard, are things like labor negotiations. And we've heard people going in and making changes to the system so that they can come back later and say, well, you really need us to come in and to hire us to come in here and help you do this because you don't obviously understand it. Well, this has not been the first time I've seen. In fact, it's actually not even about the 30th or 40th time I've seen in the last few years of scenarios similar to this, where people have gone in, they've caused these types of interruptions, and then tried to argue that they needed a job based upon that. Okay?
So a lot of times engineers are trying to decrease the amount of steam that's used in the refinery, because steam is so expensive, because you use about 40% of it towards just distillation towers. So one way to mess up a distillation tower would be to decrease the amount of steam. By doing that, you're pretty much making your distillation column just a very expensive heat exchanger. And we can't know exactly what's going to be happening inside your distillation tower without modeling it in HISIS. For example, this tower may be different than your other tower or a crude tower, et cetera. So you would do that by closing off your steam valve and
Okay, closing off your steam. Okay. So yeah, if you're going to close off your steam valve, then obviously we potentially. What are some of the other impacts that might happen as a result of that?
Well, if you are dropping the level in your tower, then if you've ever heated up your fry pan and then put water on it, it sprays a lot of water and gets heated up really fast. The same thing would happen if you're decreasing the amount of steam. Your distillation tower may be heating up, but you don't have enough level in there to be able to absorb the impact of putting in your fresh feed. So that could damage the internals of your distillation tower. And then again, if you're losing your level in your tower, then you're going to have to redo your startup, which takes a lot of time.
Okay. So again, most of these are going to end up being economic impacts and losses. But again, if 40% of the energy is being used in a facility, I can blow your whole quarter's profits by just a few little minor impacts to something of this significant. Okay, so what we've just been through there was a fairly high-level example of the type of dialogue that would happen when we were doing an assessment of this nature. But again, I think really, what is the process that we, even though this was not the level of detail that we go through, what was the process that we essentially just went through with everybody?
Well, pretty much what you want to do is you want to make sure that all of your equipment is properly sized. We say that there's the maximum allowable working pressure of the distillation tower, but you also have to remember that you have to go 150 times that amount before you can actually be leaking from the flanges. And then you also want to make sure that your pressure relief valves are going to be alleviating enough pressure so that way you aren't reaching way above your maximum allowable working pressure. And then you also have your operator rounds. Operators are going to be going around checking specific tags, checking the equipment, and operators are going to be able to hear if a pump is cavitating. It makes a really loud sound. And there are several operators that actually even know what crude is supposed to taste like. They're old, and a lot of them have died from cancer, but they still exist out there. And then you also have your manual bypasses. If a hacker goes in and closes off your control valve, you can open up the bypass around it, or if they open it up, you can close the block valves around it. And then we have the PHAs, LOPAs, which are layer protection analyses, where we associate a consequence, which would be, hey, we're going to kill 5 people from this, or we're only going to be causing an economic damage, and then how often we think this is going to happen. So you could have a $10,000 failure, but you say, oh, we could do this 20 times a year.
Okay. Right, so again, now how does this end up relating back to cybersecurity? So what we've just been through there was the standard engineering practices that any engineer is going to do at any oil and gas refinery, any similar processes, chemical facilities out there. These things already exist, and this has been part of our contention for a number of years is we already know the maximum damage in the most critical scenarios, most likely, because engineers, there's not a plant I've walked into that I can't find the oldest, crustiest, grumpiest engineer, ask him how he would blow the plant up, and he's probably going to give me 20 plans in a few seconds, because he's thought about them all at different times over the years, right? So the same thing, though. A lot of times, the maximum damage scenario is already known. The difference is, though, is that when we've modeled these from a PHA or HAZOP perspective, what they've done is they've established the criticality of the impact, but the likelihood considerations are really only from entropic hardware faults, so random hardware faults, things that happen in nature. They have not considered directed threats. So how we start to bring this back together is now we need to look at the cybersecurity steps that we need to go through in order to conduct a cyber version of this PHA or a cyber version of a HAZOP. There are several terms out there that you can see there's called CHAZOP, cyber, whatever. There's all kinds of stuff. But essentially, I'd boil this down to very simple. We go through and we look at the PHA data, we talk to the engineers, and then we start modeling what would somebody do at this step and this step and this step to cause the problem. So cybersecurity likelihood considers the directed threats as well, and it can be intentional or unintentional. Obviously, we've talked about that many times over the years. Countermeasures should include both engineered layers of protection, that's what we do that LOPA for, the layer of protection analysis, and cybersecurity controls into a comprehensive risk mitigation strategy. So for example, these are some of the things I might consider. I might consider things like disabling remote access for high safety environments. So what I mean by that, like say for example, you have a local code that says on a boiler somebody has to have eyes on the process when they make changes. Well, I probably want to make sure that if there's a remote access solution that it is blocked from any ability on the network to be able to allow connection. So I don't want somebody logging into a remote connection accidentally or at night going through and saying, I'll just go ahead and make this change from here, and then they violated code, they violated the law, or potentially, I don't know, many people in here have seen this scenario. Somebody means to be changing PLC 101 and they're accidentally in PLC 103, for example. So we want to make sure that if we know that we have a high safety threat, maybe these are some of the things we want to do. Protected virtual LANs for control messages. So I look at this saying, the data, the ability to read data and the ability to control the process often needs to be separated. One-way data diodes to allow reporting of data, but no control in some scenarios, which I know we've talked about those a number of times over the years. Encryption, mostly not for the message protection, but for the data integrity. I usually look at the data integrity. Was the command sent from a valid workstation? Was it received? Was it modified in transit? Sometimes we need to go the full confidentiality route as well, but most of the time it's for the integrity of the messaging. Man-in-the-middle protection, things like ARP Watch, intrusion detection systems. And we'll talk about that just a little bit as we move into network security monitoring. And then I would ask the question, does a manual valve mitigate cyber threats? Does a manual control mitigate a cyber threat? Most likely no, because if I learn the process well enough, I'll be able to go through and set conditions that will make you take the operation I really want you to take. So, all right, so let's say somebody actually gained all this knowledge and they were able to take control of the entire process. What if you did everything?
So first we think is it's going to overpressure, it's going to overfill, we're going to overtemperature, and we're going to relieve the flare, we're going to be spurting out the flanges, and we're going to cause a huge fire. Well, we also have to remember that this distillation tower doesn't exist in its own little bubble. Somebody downstream is going to be like, I'm not getting any feed, and somebody upstream is going to be like, why is more of my bottoms going out? So you have to think about that we need to be attacking not just this screen, but we also have to be attacking everything else down the line, and its processes aren't standalone.
And I think that's very important. So the place to bring up an important point, which is again, these don't operate in a vacuum. There are, and sometimes our greatest weakness, which are the people that we can do social engineering attacks against and things like that, also tend to be our greatest strength because they're the ones that understand if I hear this rattle, I need to go up and change this valve 1/4 of a turn. They're the ones that understand, what, like you said, what the product should taste like for whatever that sounds like. Who got that job? But anyway. So again, our people a lot of times are some of our best assets. So one of the problems that we see here is that, looking at, Dale's introduction was actually really good. What's been happening over the years is, I found the latest vulnerability for a Rockwell Siemens Honeywell controller, something of that nature. I go out to Shodan, I search a bunch of these, and suddenly I'm going to be blowing things up all over the place. No, you're not. That's not the way it works. Can you cause nuisance trips and shutdowns? Possibly. Can you cause impacts? Possibly. Are you going to cause, are you going to be able to get to this level of an attack, which is what we need to do for protection? Probably not. So we'll talk about that a little bit though. And this is just very high level, but I'll talk a little bit about how do we gain that information. So obviously, I look at like the PNID drawings. How do I do the social engineering, my open source intelligence collection? Where are some sources of data that I can find the pieces of information that I need? I will tell you from doing some of these projects in the past, it usually takes me no more than a few hours to find PNID drawings, to find process drawings, to find HMI screens. Some of the places we look for them. Going after the integrators, which most likely don't have the same level of protection as our vendors do, or our asset owners. If I'm going to go after a major oil and gas facility, connecting to them is the last thing I want to do until I'm ready to do the attack, because I don't want them to detect the attack. So I'm going to go after all the ancillary systems. I'm going to go after their third-party folks. I'm going to go after the integrators. I'm going to do everything I can to never touch one of those systems as early, until I absolutely have to, so that I decrease the likelihood that I'm actually going to be caught. So yeah, again, finding these is not difficult. Another place we find these a lot of times is on bid specifications. Sign up as a vendor for some of these companies. They'll send them out on the RFPs. You'll have the diagrams, the locations, the GPS coordinates, even sometimes things like IP addresses I've seen on the bid specifications that go out. There's lots of good data on there for folks that do it, okay? Then obviously you're going to do things like system mapping. This is not going to be as simple as launching your Nmap scans out there, okay? You're going to have to use the actual protocols and communications themselves. You're going to have to use the discovery protocols that come from a lot of vendors. You're going to need to know how to use Modbus and SIP and Ethernet IP. You're going to need to know how links and logics and things like that work. right? You're going to need to know those protocols. That's how you're going to find a lot more of those components out there online. Then I'm going to get into the initial infections and compromise. A lot of times, this is where I really first want to try to start getting onto the system and actually doing anything that might be detected. But at that point, I'm trying to establish some Bastion hosts out there. I'm trying to establish some workstations that I can actually use as to mimic HMI traffic or things of that nature. Then information exfiltration. This is folks in here know this pretty well. We're still spending way too much time trying to block stuff from coming in and not nearly enough time watching what's going out. Watching what's leaving your network is how we figure out what are those social engineering attacks that worked, what are the client-side attacks that worked, and if people are not watching the instantiation of new connections through the firewall going out, then they're probably asking for trouble. In fact, I just finished an assessment here a couple of months ago, that we actually found exactly this. They're like, oh, we have no problems whatsoever, no cybersecurity problems. And I was like, look, you've got system maps that are going out to known malware sites. I mean, there's just data flying off your network, and you haven't been paying attention to it at all. So when we get into the actual attack itself, here are some of the techniques that we might look at. Now, one of the first things I'm going to do is disconnect the operator from the view of the system. So one of the first things I want to do is suppress messages, suppress alarms, right? At least the ones I don't want them to see. All right, then some of the other things I'm going to do. Operator misdirection. Set an alarm in another part of a plant so the operators run to the other side. They don't see what I'm doing, for example, right? Obviously, I'm going to need to know this process pretty darn well. Man in the middle in HMI or deploy an RDP session. The easiest way I can think to take control of a process is to do it from the HMI. So, okay, now, however, this is a very quote-unquote loud attack. If I go onto the HMI and I hack the HMI and then I deploy an RDP server and I set that RDP out over the internet, that's a lot of network communications. There's a lot of forensic trail that are left behind potentially. That actually is a fairly loud attack way to do it. But it is the quickest and the easiest way that I could take over an HMI. However, some of the more sneaky ways might be learn the protocols, the tags, the communications themselves, and then just handcraft the packets and send them yourselves to open up valves. In that case, then, when people are investigating the HMIs, they're not going to see the commands as being issued from the HMI. They may not even notice what they're going to be scratching their heads for quite a while trying to figure out what happened. So it's a very directed way to do it. It's also a lot sneakier. And from some tests that we've done, it's also not very difficult, right? And then obviously that would be more of a TCP read and replay type attacks, for example. Obviously this is a very high level summary, but some of the things that we would consider in terms of how would we put that final attack package together, again, is what would be the various ways we could do this. So I always put at the bottom, there's a crossover point in this where the cybersecurity skills stop and the engineering skills take over. In other words, at some point in that, vulnerabilities are of no use to you if you want to try to get to the maximum type damage scenarios. You're going to have to know how to do the engineering steps. You're going to need to know the engineering protocols. So, okay, so let's move into that. Now we've talked about assessing and attacking, doing the threat modeling, understanding how we'd actually get into one of these processes. We're going to stick with our distillation column. So now, once this is up and running, what are the things that we want to do to make sure that we maintain safe and efficient operations? So I'll talk just briefly about network security monitoring for our distillation column. So obviously, some of the challenges, the network security monitoring, most NSM solutions still to date really only watch the WAN links, the wide area network links, the site-to-site communications. I was at a pipeline just a couple of years ago where they had tremendous IDS and protections on the site-to-site and the IT locations and at their WAN links. They had a Class B public internet address space for all of their industrial networks, and once you were on one, you were on all of them, and nobody would see a darn thing. So in other words, we're not watching the links we should be in many cases. Man-in-the-middle protection rarely extends into the ICS zones of control and the inter-process communications. In other words, down where I'm worried about the HMI and the PLC communications, very rarely are we actually watching for people that are doing nasty deeds down there at that level. Right? Rarely is anti-malware applied consistently, or is it up to date? This has been, I hate to be the apologist here or to bring up the old, but this is still the way it is. Right? We still don't have up-to-date antivirus. In fact, actually, one of the problems I still run into during assessments is we turned it all off because it was causing too many problems. Right? IT is often kept off the OT networks. Things like SolarWinds or some of our monitoring solutions often don't extend into the control systems environment, even though they're very good tools. Emphasis is still on the infiltration, when most ICS malware threats that are currently going on out there have a very large exfiltration component to them. A lot of them are information gathering that we've seen. They're sending data off. They're not really running the attack stuff yet. So if you're watching the exfil, you've got a much better chance of catching what's going on. Firewalls are not configured often to alert on instantiating new outbound connection requests. Obviously, take this and turn them into a positive, and these are a lot of things you should be doing. USB and mobile device security is weak. Now, okay, that said, let's say we do have a fairly good, robust IDS and NSM monitoring solution for the control network. What are some other things that we might want to watch from a control system perspective, though?
So you're going to watch your overhead temperature because that's going to be indicative of you're putting too much steam in, or if you have too many light ends up at the top, which your light ends won't be able to just cool with just cooling water. So with that, you're also going to be watching your reflux accumulator pressure, because if that gets too high, you're going to be relieving to your flare. And then the first thing chemical engineers learn how to do is a mass balance. They're going to be making sure that the amount that goes in is the amount that comes out, and then if it's not, the level should be changing. And then the lab data will also be telling you if you have too many light ends, if you're making product specs, et cetera.
Right. So now, obviously, am I going to write a snort rule or an IDS rule for overhead temperature alarm? Probably not. But what could I do? If I'm trying to implement NSM solutions, if I'm trying to implement protected messaging, what I need to do from a security standpoint is give you assurance over the data that people are seeing on their screens. So this is where maybe I go through where right now everything's just kind of the Wild West. What I need to do is I need to be looking at, okay, if these are critical alarms that I need to have guaranteed messaging and have confidence in the data, this is probably where I'm going to want to apply some additional IDS sensors, for example. I may want to apply some man-in-the-middle protection down on those devices. I may want to have guaranteed messaging. Or if I can't do any of those things, I may want to put in some countermeasures for some additional manual checks. And we've done this in a few cases. I've actually seen people that go out to check for steam. For high pressure steam, which is nearly invisible, they take a broom and they do this going into the room because you can't see it and it cuts people up, right? So that's, so in other words, there's maybe some cases where we need a manual process to verify what's going on out there. So these are all the types of processes that you have to go through in order to identify what would be the appropriate countermeasure for an individual scenario, okay? All right, so that's a little bit about network security monitoring. And then let's talk about if all else fails, and we manage not to protect the process despite our best efforts, because as we know, hackers, right? They're pretty good at what they do. Things change, they learn new tricks, and sometimes stupid human tricks, all kinds of other things can happen. So we always want to prepare for the worst case scenario. So we're doing it from a forensic standpoint. Let's say that we are called in. This would be an example. Lily and I have talked about this. You and I are the ones that are called in to respond to a particular incident. What are the things that you would look for? What are the things that I would look for? How do we combine those approaches to an overall solution into knowing, okay, where was it? Colonel Mustard lead pipe in the study. How do we figure that out? So sources of evidence collection from an IT perspective, this should look fairly, or from an OT perspective, this should look pretty familiar to most folks. We want to make sure we get an inventory of all the relevant systems. This includes the manual processes, because a lot of times people will have things like paper travelers that they sign at shift change, or shift notes, or operator workstation notes, lab notebooks, that kind of stuff. We want to make sure that those are also included. Engineering workstation and manufacturing enterprise system, controllers, drives, historians, HMI clients. Don't forget the mobile devices. The bring your own device revolution, quote unquote, has brought us all kinds of things like people that control their drives with their Nexus tablets, right, through Bluetooth. So anyway, remember not all components are online or network accessible. There's often physical relays. And the power utilities is the area that you really want to focus on, because a lot of times there's physical registers that happen that are great sources of information that the engineers will go out and to look at, but they never report back to the folks that may be investigating the incident, right? They're often physical relays, physical alarms, other sensors relevant to an investigation. A lot of time I am just trying to associate the fact that somebody was at that workstation. So badge readers, camera systems, proximity sensors, anything else that we might have out there that say there was somebody here at this time, and then I'm trying to figure out, was it a person that issued that command? Was it a mistake? Was it an electronic message that was sent outside of that? So in other words, consider everything as we're going through this. This is not an IT forensic investigation only. Your engineers and operators are going to be key to success as well. So sticking with our distillation column, what are some additional things that the engineers will be looking for?
The first thing that they'll go to is their historian. My experience is with Pi. They're going to look to see if there's any sudden changes in the data. So if the hacker doesn't change all the data in the historian, then you're going to see, oh, our steam valve just shut. Why would it do that? And then you would also look to see if the hacker did change the historian, if the data didn't match the incident. So you would know, oh yeah, we definitely had an overpressure, but our pressure alarm didn't go off. Was there a problem with the pressure transmitter, or maybe was there something else? And then you're going to talk to your operator and say, well, did you close that steam valve? Or what happened? Did you hear anything? Did you smell anything? And then you're also going to be checking with the lab to see if they have any results and say, oh, well, there was light ends in the overhead, or they didn't collect a sample at that time.
Right. And again, what we're looking for is, we've talked about this, and we've not had to do a forensic investigation yet, so we've kind of, as part of this presentation, have done some bouncing off of each other here a little bit. Well, what would you do here? Well, what we came up with is yes, you know, a lot of times what I'm looking for when everybody's pulling all, like, let's say I'll pull all the files, the A time, M time, C time, all that stuff in a 15-minute window, look through what all those operations were, look for all the registry operations, look in the backup registry. I'm trying to figure out what people did at different times, to correlate operator actions. So obviously, you know, again, what I'm looking for though is you know, that's all well and good, but there's lots of other sources of information. And very often, there's going to be, it's the last slide, so. Very often, there's going to be discrepancies between one or more of these systems. Those are going to help us establish very well what are the potential affected systems, where are those discrepancies, and then start narrowing down which ones were actually impacted for us to be able to sort out what was actually compromised, what did the cyber attacker potentially do. Was it all cyber? Was it an inside job? Was it a social engineer? But again, the incident responses I've been on, very rarely is this level of a step taken. And as I tell folks, I'm like, unless you're willing to take this step, there is going to very quickly come a point that the data collection I'm doing is going to cease its effectiveness. Hopefully I can tell you something in that time, but unless you're willing to take this next step, you're really not going to have a really good understanding of what's happening. Of course, obviously, then we get all the other problems out there, like, for example, you know, they've kept running the process for 3 months before they finally called somebody out, and by that time, the data is pretty much stale and useless. But anyway. So with that, so again, we've kind of gone through really the life cycle of managing a distillation column if you're looking at it from a cybersecurity and engineering perspective, from assessment to how we would monitor for the safety and efficient operation of one of these, and again, if the worst happens, what would be the ways that we would actually try to figure out what happened. So with that, we can turn it over for any questions. Too early in the morning, right?
Marina Krotofil, European Network for Cybersecurity. Thank you very much for this presentation. Really amazing presentation. I'm working on a similar topics, and right now my scenario is catalyst poisoning. And like, since I already went through this stuff, like what can I switch on, what can I do? What now I'm doing, and my question whether you're trying to do the same. I was trying to quantify what are the efforts of the attack in comparison to the effect on the company. So for example, for me, it turns out that most of the scenarios where I develop, they tend to be more expensive that I'm damaging the producer. And it's like, well, I have to go like further. And then suddenly, like because the process is integrated, suddenly I have to suppress so many alarms, so the attack becomes so expensive that I actually have like thinking like, maybe I have to pick up another scenario. Like, did you try to quantify those attacker efforts via consequences?
Right.
Versus?
Yeah, that's a good question, actually, and it's something that we kind of meant to cover more, and we just ran more out of time, because the idea would be anything that we're doing here is going to feed into a larger risk analysis where you're going to identify countermeasures, those kind of things. So it's kind of the outrun the bear methodology. I don't have to outrun you, I just have to outrun the bear. Or excuse me, I have to outrun the bear, I just have to outrun you. Said that backwards, sorry. And the idea there being is that, you know, I'm trying to make my target the least attractive of them out there and let somebody go after somebody else's. So there again, when I'm looking at these various countermeasures, that's exactly what we're looking for, is how complex of an attack is this? Is this an attack somebody could launch completely remotely? That's going to change my entire countermeasure strategy than if it's one that's going to require absolute physical access and somebody going out and pre-staging the attack for me. So obviously, we're trying to figure out through that process what is the level of complexity, what's the level of technical skill required, is it going to take engineers and IT folks, or can an IT, you know, again, what are all the things that are going to go into that? And we're going to feed that into a likelihood matrix, which we kind of hinted at, but we didn't get into too much. What's the likelihood of attack? And that's going to drive my countermeasures heavily. So, you know, am I going to disable all remote access, just call it done? Am I going to put some manual valves in? Am I going to put in maybe a backup light bar, or excuse me, like a light pole or something like that onto a safety system, so that that safety system is modified, I see that, and it's totally non-network. You know, those are all the types of things we're going to go through. Going through this process helps us flush out what are the fit-for-purpose countermeasures for an individual risk. Okay.
Okay, if you have any questions, you can also send them to s4question@digitalbond.com. Is there a next question?
Hi, this is Mike Tucker, formerly Digital Bond, now somewhere else. The question I've got is that you actually brought up media and mobile devices, all right? And so you brought up tablets and other things, smartphones. Okay, yes, we're using cameras. Yes, we're doing this. All right, what about the stuff that's already been in the plant for years?
Right.
Altimeters,
Right.
heart calibrators.
Right.
All right, things that we use to actually verify that the equipment is in proper working order, that we're actually using to make the judgment call, like in things in the chemical lab. How does that fit into a PHA, or would it fit into a PHA?
Well, the thing that operators use for their rounds, at least in the company that I've worked with, is a little computer device where they'll scan the barcodes and they'll keep track of all the different data. So you would definitely need to make sure that those don't leave the refinery, because those would contain a lot of data.
Yeah. And I think absolutely, I think that's, you know, I will confess, and like a lot of the assessments that we've done, that's an area that I'm still just trying to get my head around, because again, there are just all kinds of little pieces of test equipment and lab data out there and things. So yeah, a lot of times when we've done getting out of the risk analysis and to more of the long term, when we've done some more of the business continuity and disaster recovery work, that's where we've started asking a lot more of those questions about, okay, what are all the tests you use to figure out what, and so what, you know, to figure out what's wrong with the product. So if we start writing a DRP plan, for example, it might be, say, what lab tests need to be performed. And I know that the utility I worked with last year, that's one of the things that we started getting into finally, and that was really the first time I think we had gone through that. So again, if we're talking about what next, I think that's something, you know, again, there's a lot of data out there for NSM and forensics that exist. We just don't necessarily know to go collect that for doing the job that we do. And so, yeah, I think that's got to be included. The other problem I've seen is how many of those, just as an ancillary note, how many of those systems are networked and they still run on things like DOS or Windows, and they're highly vulnerable. And so, yeah, there's other problems with that equipment that have to be considered. So, yeah, there's been a few cases we've recommended either upgrades or taking those components offline or other protection mechanisms because, hey, look, this is a key part of you figuring out what happened if something does go wrong.
Okay, my name is Jeff Hahn with GE, and perhaps to take this to a even more realistic and relevant thought, as you were talking about all of this, what was going on, the distillation column, and overflow and stuff like that, my mind kept going back to the BP Texas City explosion.
Well, really, the problem with the BP Texas explosion was that they did overflow their tower, but they were putting all of their overflow into a bin that vented to the atmosphere, and instead that needed to be venting to the flare, and that needed to be burnt off. So since the overflow, the vessel that they used overflowed, and they were venting all of that to the atmosphere, that was this part that caused the problem, not the overflowing of the distillation column.
And this was also during startup, so the mass balance wasn't necessarily being looked at as much or as closely because things were starting up and there was fluctuations.
Yeah, the operators were ignoring some of the alarms that were going off. They had some alarms that were faulty, but that definitely needed to be a problem in the procedure also.
And this is what we're finding, that as we're doing assessments, adopting more of this type of methodology we've been talking about today, one of the questions we're asking is even plants that have not been necessarily required to conduct a PHA, we're going back and we're having them do at least a PHA light, just for that very reason, is have they thought about these? And for the places that have, like some of the oil and gas refineries, we are seeing folks that are going back and considering new layers of protection that they had not previously thought about, just because, again, like the BP is a great example because of what I would call a loss of view type scenario. They no longer had an accurate representation of what was going on, so people were taking actions that were counterproductive to their continued existence. There again, we want to make sure that we're increasing, this is an overall risk management process, right? And so, through what we're hoping is that through both the engineered layers protection analysis and the PHAs and HAZOPs, and now the cybersecurity PHAs and these additional assessment steps, that what we're doing is we're raising the bar for risk against all types of risk, not just somebody doing it from a cybersecurity perspective. But that's an example. I actually thought about using that one in here, and that is a very good example of kind of what we're talking about. So, absolutely. Okay?
Okay, I